How to interpret CFD results for fluid flow regimes. Imagine you're looking at a computer simulation of water flowing through a pipe. The colors, patterns, and numbers tell a story about how the fluid moves. But how do you read that story? How can you tell if the flow is smooth or chaotic just from the results? That's what we're here to figure out. First, think about the different types of flow. When water moves in a smooth, orderly way with layers sliding past each other, that's called laminar flow. It looks calm in CFD results, with smooth velocity contours and little fluctuation. You might see uniform color patterns indicating steady flow. On the other hand, if the flow is chaotic with swirls, eddies, and mixing, that's turbulent flow. In CFD visuals, turbulent flow shows irregular velocity fields, vortices, and complex pressure variations. Between these two is the transition flow, where the flow starts to become unstable. CFD results here might show a mix of smooth and fluctuating features, depending on the flow conditions. To interpret CFD results accurately, start by examining the velocity fields. Look at the velocity magnitude and direction plots. If the velocities are steady and uniform, you're likely seeing laminar flow. If they fluctuate wildly, turbulence is probably present. Next, check the Reynolds number, which is a ratio involving fluid speed, characteristic length, and fluid viscosity. Low Reynolds numbers usually mean laminar flow, while high numbers suggest turbulence. CFD software often calculates this number for you, or you can compute it yourself. Flow patterns are also key. Use the CFD visualizations to identify vortices or recirculation zones. These features are signs of turbulence or complex flow regimes. Pressure distribution is another clue. Laminar flows tend to have steady pressure gradients, whereas turbulent flows show more irregular pressure changes. For unsteady flows, look at how the flow evolves over time. Transient CFD results reveal if the flow switches between regimes or develops instabilities. Remember, CFD can predict average velocities and complex flow structures well, but it has limitations. Capturing very high turbulence or interfaces in multi-phase flows can be tricky. The numerical methods and grid quality also influence the accuracy of your interpretation. In mechanical engineering, understanding these flow regimes from CFD results helps optimize designs. It ensures smooth flow, reduces vibrations, and improves thermal performance. By carefully analyzing velocity, pressure, flow patterns, and Reynolds number, you can confidently classify the flow regime and make smarter decisions for your projects.